Sorry for the delay. Good evening, everyone. I am Mansi, co-author of the paper termed on molecular dynamic simulation of H-crack propagation in CHS shell under direct bending. This is the overview of the presentation. Introduction to concrete. Concrete is a widely used construction material composed of cement, aggregates, and water. It has a complex multi-scale and multi-phase structure across different scales and exhibits quasi-brittle fracture under different loading conditions. Interaction of various components at different scales govern the overall behavior of concrete. The multi-scale analysis of concrete is done at various scales. At macro scale, concrete is characterized as a homogeneous material responsible for long-term durability properties. At mesoscale, the interaction between aggregate, cement paste, and interfacial transition zone are critical to structural performance. Nanoscale or atomic modeling deals with the interaction of hydrated cement compounds with other particles. Nanoscale modeling can be used as a time-effective and economical alternative to experiments. The figure shows the schematic representation of the concrete at macro scale, mesoscale, and atomic scale. CHS gel, calcium silicate hydrate, is the major binding phase consisting about 60% of total hydration products. It plays a crucial role in determining the mechanical durability and overall performance of concrete. CHS gel is majorly responsible for providing concrete with its strength and stiffness. Material characterization techniques reveals that CHS gel has similarities with tobermorite. Tobermorite supergroup is the classification of family of minerals with a layered structure similar to clays. To get a desired CaSi ratio for CHS gel, SiO2 groups are randomly removed and water is absorbed in the dry tobermorite structures. The figure shows the atomic structure of unit CHS cell taken from the Zhang et al. Molecular dynamic simulations are computational technique used to model and study the behavior of atoms and molecules over time. It provides detailed insight into the behavior of metals at atomic and molecular levels. MD simulations are versatile and widely used to explore the phenomena that are difficult or impossible to explore experimentally. Crack propagation in materials is multi-scale phenomena and occurs by breakage of bonds between atoms. The molecular simulation of cement-based material is an effective approach to study the properties and interactions of cement system at a fundamental scale. However, the complexity of concrete at larger scale and longer time frames still poses challenges for MD simulations. The principle of MD simulation is based on the Newton's second equation of motion. The initial atomic position and velocity and their interactions between the particle gives the force and the acceleration is calculated through it. For every accelerated step, the initial position and velocities are updated and the same procedure is repeated over the desired number of steps. The procedure for MD simulation requires the data file input script containing information of initial position and velocities, a boundary condition, basically periodic and non-periodic. Periodic boundary conditions assume to have element entering box from leaving from one side and entering from another side. The force field are the energy interactions which define the atomic reactions over the system. The ReXFF simulation force field is used to here and it is capable of simulating fracture and formation of chemical bonds. The total energy in ReXFF is some combination of different atomic level energies. After getting a proper system, the energy minimization is done to minimize the potential energy of the system, and the most common procedure for that is the conjugate gradient method. The thermodynamic ensembles are provided on the system using microcanonical, canonical, and isothermal isobaric ensembles. For deformation, the loading rate is applied in any desired direction with desired values. The resultant post-processing of the data is done in can be either done in OVITO, MATLAB, or Visual Molecular Dynamics. Motivation for the study: the nanoscale modeling has potential to delve deeper into the failure mechanisms and provide the foundation for enhancing material properties. Till now, the mechanical properties of CHS shell under uniaxial and biaxial loadings have been explored. Use of MD to understand the atomic breakage of CHS gel from the perspective of fracture mechanics is necessary. Here, mode 1 fracture properties of CHS gel have been explored under 3-point bending test. Fracture characterization has done on the CHS gel from the perspective of MD. Methodology. First, the atomic modeling of CHS cell. The unit data for unit cell of CHS is taken from Zhang et al. The figure shows the atomic structure of CHS unit cell with calcium ions represented as green, oxygen as red, silicon as beige, and hydrogen as white. The CSI ratio in this unit cell is 1.64 and with the respective density is 2.24 gram per centimeter cube. To get the desired size of structure, the unit cell is replicated in X, Y, and Z direction to get a final beam-like CHS structures with the dimensions of 27.5 angstrom in A, X, 228.0 angstrom in Y, and 45.8 angstrom in Z. The simulation procedure. Firstly, the initial molecular model is geometrically optimized by conjugate gradient algorithm with the energy tolerance value kept as 10 to the power minus 6 kilocalorie per mole and force tolerance value kept as 10 to the power minus 6 kilocalorie per mole angstrom as per the literature. The system is brought in equilibrium by using isothermal and isobaric ensemble with temperature of 300 Kelvin and pressure of 101 kPa. The equilibrium is carried out for 300 picoseconds under periodic boundary conditions. EXFF force field is used to describe the inter and intramolecular interactions. Large-scale atomic molecular massively parallel simulator LAMS is used to perform the MD simulations in the present study. Post-processing of results is done in Open Visualization Tool, Obito, and MATLAB. After getting the system in equilibrium stage, a pre-existing void is induced in the CHS model as an H crack. Through the thickness crack with 5 angstrom width and 9 angstrom height is made by deleting the atoms. Non-periodic boundary conditions are then imposed for the load application to avoid filling of void with other atoms. In X and Y directions, non-periodic string trap boundary conditions are used, while the Z axis have fixed boundary conditions. The simulation of three-point bending has been done by fixing the ends molecule for ends atom for 30 angstrom distances as fixing, and the rest of the system has mobile atoms. The middle 50 angstrom part is kept for the loading region, and a load of 0.15 piconewton has been applied. Results. The displacement profile for CHS beams under bending is shown. The simulation is aborted after a time period of 1095 picoseconds due to the computational restrictions. As the loading progresses, the crack opening displacement increases. The oxygen and hydrogen bonds are primarily responsible for the crack widening. With the increase in simulation time, the bonding and debonding of O and H atoms is observed. The atomic shear strain profile shown in figure 8 of CHS gel under bending stresses. Initially, majority of the atoms experience little deformation. As the crack growth with time, the strain localization becomes more and more prominent. As the loading progresses, the higher strain regions intensifies near the notch tip as shown in figure 8b. However, at the atomic level, the overall shear strains are almost uniformly distributed throughout the span. The y-direction displacement contours are shown here. A typical macro-scale bending behavior is also observed at the atomic scale. Localization of large displacements near the crack tip indicates progressive fracture. The displacement contour highlights the structural response of CHS to external bending forces, which is crucial for understanding the failure mechanisms in materials under load. Next figure shows the movement of atoms in Z direction with symmetrical displacement profiles at beginning. The top layer experiences the largest deformation with maximum deflection around 1.7 angstrom. At the latest stages of loading, the overall displacement of the specimen increases. The progression of out-of-plane displacements during the bending is highlighted. The image shows how the atomic velocity fields evolve as the bending progresses. The interlayer water present in CHS gel is more likely to get displaced during loading, hence resulting in formation of voids. The atoms near the notch experience higher velocity due to the increased deformation or stress levels. Atomic rearrangement occurs near the notch due to high velocities of oxygen and hydrogen atoms. These atoms are most likely to debond first as seen from the bending profile also. The fracture characterization, the energy release rate for CHS gel is calculated by the formula where GC is the change in free surface energy. The surface area after the crack propagation is calculated by surface made modifier using in Oviedo, and the area under stress strain curve is calculated for the energy. The fracture toughness is calculated by the Athens formula. The stress strain curve for CHS gel under bending is shown in figure 12. The spikes in the stress strain curve is due to the continuous bonding and debonding of atoms at the molecular level. The calculated values of fracture energy and fracture toughness are 1.41 joule per meter square and 0.31 MPa under root meter respectively. These values are obtained in range with the literature findings. The crack opening analysis is done to understand the pattern of crack opening displacement with the time. The graph shows a linear increase in COD values. Due to computational restrictions, the complete failure of beam sample has not been achieved in the present study. The increasing initial pattern for COD agrees well with the reported literature and can be used for the further study. Concluding remarks, the bending behavior of CHS gel has been simulated using molecular dynamics. The findings highlight the role of atomic structure on the deformation behavior. The presence of interlayer water in CHS is primarily responsible for failure. Atomic bonding and debonding is observed near the notch tip, which delays the progression of crack, resulting in overall quasi-brittle behavior of concrete. The MD simulation successfully captures the mechanical and fracture behavior and shed lights on the phenomena happening at nanoscale. These are some of the references used for the study. Thank you for your kind attention.